More questions? No? Okay.
No.
Thank you, Brandon.
Okay.
So, will you find the way?
Yeah.
I'll help you.
Okay.
So, the next speaker is Levi Talk, who will help us to recall main ideas, and maybe he will tell a couple of words about applications of so-called time-independent perturbation theory. Floor is yours.
Thank you all for coming. So I'll be talking about time-independent perturbation theory, mostly of the theory behind it. So first, this is mainly used in problems that you cannot solve exactly, but you can relate to a problem that you can solve with high accuracy. So that is H naught, and there's some correction that's H prime, and this lambda is like a scaling parameter, so you can ramp that up and down depending on your how much deviation you have. There are some assumptions that your H prime and your H naught are somewhat similar. They're not like they won't give you totally different answers. Your eigenvalues are known for H naught, and then your eigenvalues and eigenfunctions do not greatly deviate from your H prime to H naught. So to expand the wave function, we do it in like powers. So the first term is 0 power, then first, second, third, and you can go as many powers as you want. Most of the time, people do first and second perturbation theory, and when you plug in your Hamiltonian acting on your wave function, you get your eigenvalues and your eigenfunctions back, and you have to do some algebra to get your eigenvalues. But for the first order correction for energy, it is just the expectation value of the unperturbed wave functions, where your Hamiltonian is your perturbed wave function, and then your the correction for your wave function is a similar term divided by the difference in the energy of the m and n state times your unperturbed wave function. So with this, you can get different values. Like you could do dispersion. So if you want to try and figure out van der Waals interaction, you can choose your H prime to be like 1 over x to the 4th, or x is some number, and then you can pull out your correction, and then you can hopefully get an analytical solution. And that's what is typically done in a lot of like DFT functionals. So in conclusion, perturbation theory can help solve very difficult or impossible problems by connecting your unperturbed wave function and your perturbed wave function that act similarly on the system. And then you can get first order, you can do second order, third order, but I just showed first order today. So then these are what we talked about. In this presentation, I did not go over degenerate cases. For degenerate, when your energies are the same, so like d orbitals, I presented on this when we did it in the class. You solve everything and then you just pull out the blocks that are degenerate. So if it's d orbitals, then you pull out the d orbital and you manipulate that to get the energy splitting. So are there any questions?
Okay, let's thank Levi for a brief, but very dense presentation.